Wow, look at those graphs. Okay. Do you see some patterns? Let's start with the first columns. Actually, the first and the last graphs. What do you notice about the first and the last graphs for each set? Yes? There, Ronnie?
The first and the last graph are the same.
Okay, so let's make some conjectures. First conjecture, the first and the last graphs are all the same. So if we generalize that, and what will be our addend? For the first graph, it's always 1. Okay, n1 is equal to n. Okay, n minus 1. And their graphs would look like, what can you say about their graphs? This looks like a triangle, a square, a pentagon. So they look like, yes, polygons. Convex polygons. Actually, if you have placed the points equally spaced around the circle, you form regular polygons. Okay? So this is actually convex polygons of side what? Okay, that's correct. Side n. Very interesting. How about other observations? What can you say about 5-2 and 5-3? 6-2 and 6-4. Here, 10-2 and 10-8. All right? 10-6 and 10-4. Here, 11-3 and 11-8. All right? Here, 12-9 and 12-3. What do you notice? They're all the same. So, can you make a generalization? Another conjecture? And, yes, if we want it to be k, this will be equal to which one? N, yes, the modulus is still n, and the addend is n minus k. All right. What else do you notice? Any other observations? Look at the green ones. The middle portions of the green ones. What can you say about the green ones? The green ones are the 4, 6, 8, 10, and 12. So if our n is even, what can you say about n, the middle ones? 4, 2, 6, 3, 8, 4, what's next? 10, 5, and 12, 6. What can you say about the graph? Okay, the addend is n over 2. And how do the graphs look like? They look like a pizza. Okay, they're actually a set of, what do you call these lines? Intersecting lines. Well, we're talking about circles. So what part of circles? Okay, they look like a set of diameters. Okay. Other observations? When do you get piqued stars? Piqued stars? Piqued. Those that you can construct without lifting your pen? Were there graphs that you were able to construct without lifting your pen? No? Continuously from 0, ending in 0 also? Which are those? Is it when n is odd? Which ones are those? Let's see. Who did 7-2? 7-2 was done continuously without lifting the pen. Okay. And so was 7, 3. 7, 2, 7, 3. And of course, 7, 4 because these two are equivalent. And 7, 5 as well because it's equivalent to 7, 2. When do we get picked stars? Is this a picked star? No, you didn't draw them continuously. 8, 3 was done continuously. And so it was 8, 5. Here, which ones were done continuously? 9, 2, 9, 4, and of course their partners 9, 5, and 9, 7. Here, which were done continuously? This one, 10, 3, and the partner 10, 7. How about 11? Yes, 11, 2, and the partner, 11, 3, and the partner, 11, 4, and the partner, 11, 5, and the partner. So can you make any generalizations? What can you say about this number here and this number here? Does it have something to do with odd and even?
Yes.
Huh? Let's see. We have 9, 2, 8, 3, 9, 5. 9, 2 was done without lifting the pen. 9 is odd, 2 is even. 8, 3 was done without lifting the pen as well. But 8 is even and 3 is odd. I don't think it has something to do with odd and even.
Relatively prime.
Yes, Ronnie?
The graph would be a picked star whenever the n and its addends are relatively prime.
And the addend here, for example, let's denote it by D. Okay.
N and D are relatively prime.
N and D are relatively prime. Meaning, they're relatively prime. So, since this is smaller, does this divide the modulus? No. Okay. So, our D, if D does not divide the modulus, right? We get picked stars. Okay. And any more observations? Any more observations? What if D divides the modulus? For example, we have 8, 2 here. Our D divides the modulus. Here, 3 divides 9. What do we get? Here, 3 divides 12 and 4 divides 12. What do we get? Let me highlight it first. So when we did 9, 3, we were able to form this. That would be 1. This would be another 1. And this would be another 1. So how many figures, how many distinct figures were used? So we were able to get 3 polygons, right? 3 polygons of side. What's the side 3? Because they are triangles. All right. How about in where? 10, 2. Okay, 10, 2. 10, 2. How many figures, independent figures were used? This one. Oh, where is it? Here. That's the first one. And here's another one. So we were able to form 2 polygons of side 5 each. How about here in 12:4? Okay, you were saying 4. May I ask Migs to highlight the 4 polygons that can be formed? Okay, that's 1. That's 2. Red again. 3. And, 3. 4. Where's the fourth one?
The red one. The red one.
The red one. Okay, so we were able to produce 4 polygons, each of side 3. Okay, so how do we generalize that? If D divides N, what do you form? The graph would have how many polygons? D polygons of side N over D, N divided by D each. Okay? Does that cover everything? D divides N. If D divides N, 4 divides 8. Will you get D polygons of side N over 2 each? No. So what's wrong with our generalization? There must be a restriction. Except when? Okay, except when N over D. So if D divides N and N over D is not equal to 2. I'm sorry, let's change that. N over D is not equal to 2. Right? Actually, you can find more interesting patterns and you can make your own conjectures and eventually prove them. Okay? What's interesting to note is that when we talk about multiplication, we don't follow the same patterns. So let's have an example. We will use the brackets this time to denote multiplication. So if I have 10, 5, that means I'm working on Z10 and 5 is my factor. So it's not the addend anymore. So I'll be needing, but before that, let's construct the multiplication table for 10. Let's concentrate on 5. What is 5 times 0? 0. 5 times 1? 5. 5 times 2 is 10, but we're working on zeta. This becomes 0. 5 times 2 is 15, but 15 is congruent to 5. 5 times 4 is 0. 5 times 5 is 5. 5 times 6, 30. 5 times 7, 35. 5 times 8, 40. What's this? 0. And 5 times 9 is 45. That will give you 5. Okay. Are you ready to do multiplication graphs this time? Yes. Okay. So you work in the same set of 3s each. So group 1 will do the blue. Group 2 will do the peach. The green one. Orange for group 3. Group 4 and green for group 5. Okay, here are the instructions. Are you ready to show us your work? Yes. Okay, group 1, can you show us your work? What did you do? Can you post your colored papers on the board? We need markers.
Okay.
Here. Put here.
We are asked to find different values for n and factor n minus 1. And we found out that for the given graphs we have parallel chords, and then if n is even, it is equal to n over 2 minus 1 parallel chords. And then if n is odd, we have found out that n plus 1 over 2 minus 1. And so we have here the graph. For n is odd, for n is even, so it is n which is 20 over 2, so 10 minus 1, so 9.
9.
1, 2, 3, 4, 5, 6, 7, 8, and 9.
Okay. How about if n is
Parts.
odd?
And then if n is odd, so let's take for example 23 plus 1, and then 22 over 2 is 11.
23 plus 1 is 24.
24, so
24 over 2.
12 minus 1 is equal to
11.
11.
Can you show us 11? Is it really 11?
So
Can you
let's
count?
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11.
Very good. Okay, let's give group 1 a big round of applause. Alright. Can we have group 2? Group 2, please. What were you asked to do, group 2?
Our group were asked to give different even values for n and n over 2 minus 1. And we found out from the graph that the graphs are parallel and perpendicular. So for the first graph, for n is 24. So the factor is 24 over 2 is 12 minus 1 is 11. So the graph are parallel and perpendicular. For the next one, we are asked to give different even numbers for n and n over 2 plus 1. And we found out that on the graphs are diameters. So for the first one, n is 6 and n over 2 is 3 plus 1 is 4. So the graph is diameter.
Okay, so very interesting. Let's also give them a round of applause. How about the third group? Group 3? Oh, who's your partner? Okay. Oh, we have another set of interesting graphs.
So we were asked to give different even numbers and graph and with the factor n over 2. And we noticed from the graphs we have made that it looks like set of chords coming from point n over 2 and or point 0. So if n over 2 is even, the number of chords is are n over 2 plus 1. So in our example, 16 with factor 8. So n is 16 over 2 is 8 plus 1 is 9. And the number of chords coming from n over 2 is 1, 2, 3, 4, 5, 6, 7, 8, 9. And coming from point 0, n over 2 minus 1. So we have, in this example, when our n is 20 over 2 is 10 minus 1 is 9. So coming from point 0, 1, 2, 3, 4, 5, 6, 7, 8, 9.
Okay. What if n over 2 is odd?
And if n over 2 is odd, point n over 2 and point 0 the number of chords coming from point n over 2 and point 0 are the same. So it is n over 2 minus 1. So from here, our n is 10, over 2 is 5, minus 1 is 4. So we have 1, 2, 3, 4 chords.
Okay. Isn't that interesting? Let's also give group 3 a big round of applause. Okay? All right. Thank you. By the way, we have to take note here that our n's here are even, huh? N are even here. And also here. But for the first group, there was no restriction. Let's see the work of group 3. I mean group 4. Where's group 4?
We are asked to find the graph of n factor n minus 1 all over 2. And we have noticed that the graph of n with the factor of n minus 1 all over 2 is a 6-pointed star. So, we also noticed that if you can have this one and we subtract 2 from n, we can also have a 6-pointed star graph. For example, this one, 9, 4. It has a 6-pointed star graph. We can also have 9, 7 as the same, which have a 6-pointed star graph.
Okay, that's certainly interesting. Another round of applause for group 4. Do you see the 6-pointed stars? So this is 1. So I'll shade them so you will see. This is 1 6-pointed star. And do you see the same star here?
Yes.
Where is it? It's actually here. 1, 2, 3, 4, 5, 6. And here, do you see the 6-pointed star?
Yes.
Where? Can you shade them, Fran? There are many 6-pointed stars in that circular graph. Okay, that's 1. Another. And may I ask somebody to shade the 6-pointed stars in this graph? May I ask Migs? The taller ones. So how many 6-pointed stars do you see? Many. Okay, can you shade just a few? All right, that's another 6-pointed star. How about the one on the left? Yes. So how many 6-pointed stars do you see? 1, 2. So far, he's shading the 4th 6-pointed star. Isn't that nice? Okay. Actually, as n increases, the number of pointed stars or 6-pointed stars also increases. Okay. There's another one?
What if they intersect?
They're not 6-pointed stars. Some are intersecting, yes. Okay, maybe you can stop for a while. That's clear enough. We have seen many 6-pointed stars already. Okay, can we have the last group? Another interesting graph. What will you show us?
So our group was assigned to give different values for n which is greater than or equal to 19 and graph n2 and n3. So for the first case, we let n as 49 and 25. So after graphing, we found out that the graph of n with factor 2 is cardioid. While in the second case, we let n as 69 and 43. After graphing, we found out that the graph of n with factor 3 is something that look like two hearts that are combined.
Okay.
That's
Isn't
all.
that interesting? Also, another round of applause for okay. Actually, for this one, the restriction was n should be odd. Am I correct? N should be odd, and it should be greater than 7. And here, our n should be greater than or equal to 19. So if it's a 2 here, you get cardioids. If it's a 3 here, you get an epicycloid with 2 cusps. We also call them as nephroids, right? Those are very interesting. Actually, these were all discovered by a grade 8 student in the late 90s. The student's name is Brain Foggy. No? So it's still open for explorations. There are many other interesting discoveries regarding circular graphs. All right? Did you enjoy our session? Yes. So, for your assignment, I want you to make your own graphs. I want you to be a bit more creative. You add more color and use your imagination. I want to show you the works of my former students. You can do something like this. Okay. I hope you enjoyed today's session. Okay, so I'll see you all next meeting. Goodbye, class.
Goodbye, ma'am.